Hello, everyone. Today we are going to continue the discussion on the uncertainty analysis lecture, and essentially we are going to finish the lecture on the uncertainty analysis. And oh, let's get to the point in the lecture. Yeah, so we covered essentially what is the estimate and what's the difference between estimate and the true value, what's the difference between precision and accuracy, and all of those things. But the next step is to find the uncertainty. What is uncertainty and how can we find it? So we have talked about what uncertainty is, but we just want to talk about it in more detail and find different methods of calculating the uncertainty. So essentially, the uncertainty is can be assumed to be the probability of occurrence of your estimate or occurrence of an observation, the probability of the occurrence of an observation. And to explain probability a little more, we can go back to the classic case of coin toss, tossing a coin, which is essentially the probability of the face or the back of the coin is the frequency of occurrence of one of the sides, and it's going to be the same for both face and the back if you do the tossing, if you do enough number of tossings, a large number of tossing. So the likelihood of getting a face and a back is equal to each other and is both 0.5 or half, right? So find this probability is the main goal of in the uncertainty analysis, right? We want to use a normal distribution, all of these techniques, like Gaussian techniques or student T techniques, to find this uncertainty part, which is one of the main points of this type of analysis. Okay, but before getting there, we have to talk about the probability distribution a little bit. I want to talk about that distribution by giving you an example, by explaining it through an example. Let's say we want to toss a horseshoe at a distance, right? The first thing you want to do is to estimate of how far it will go overall, which is going to be your estimate, right? The average value, the arithmetic mean in most cases for us, right? And then let's say you have many tosses. Let's say you have 99 tosses, essentially 99 throws, okay? And you measure the distance of each toss from this estimate, right? Let's say toss 1 at this distance, toss 2 at this distance, and you do it 100 times. What we can do is to present this data with a histogram. Histogram is how you present your interval data. Let's say we make intervals of the distance from the target, right? 0 centimeters from the target to 10 centimeters, 10 to 20, 20 to 30, 30 to 40, and so forth, and so on and so forth. What you're going to get, and then put the number of throws that meet this interval in each column, essentially. Okay, and if you plot this, you will get something called a histogram. Okay, we can change the intervals from every 10 centimeters to every 20 centimeters, and you will get a different histogram, but they look very similar to each other. As you can see, the only difference is that the accuracy, I don't want to use the word accuracy, but it is your first plot with a smaller interval is more detailed, if you will, and it gives you a more detailed representation of your data. Sometimes you need this detail, sometimes you don't, so you can choose and go forward. Okay, so essentially, as you can see, you can compare. This looks like a distribution. Okay, not exactly like this, but something like this. This is a skewed distribution, as you can say, and this is essentially the basis behind the probability calculation. So this distribution represents a probability of one of these intervals happening, right? Most important or most famous probability distribution that we have in statistics, and that is the representation of the real world, is the normal distribution. Essentially, how your data will distribute. If you were tossing this coin, as far as the distance goes, this would have been your inner bar. If you do it like a million times, okay, you will have the normal distribution. And each part of this plot will represent a probability of an observation X happening. We have different types of distributions. The most famous ones are the normal or Gaussian distribution, and also T or a student distribution. It's called the T student or a student distribution. We will then these two distributions will be the focus of our lecture and the focus of the lab. We are not going to go into skewed distributions and all of those things. We're just going to deal with the normal distribution. So the idea is that if you want to go back to the horseshoe toss example, the idea is the distribution of the distance from the mean essentially looks like this, right? Okay. And for the normal distribution, if you want to talk about the normal distribution, we can find the probability of each observation using the equation of this line, which is presented using this. That's P of x, 1 over sigma square root of 2 pi e to the power, or exponential of negative x minus x of m squared over 2 sigma squared. And you have to keep in mind that sigma here is the standard deviation. And it is obvious from this plot. So essentially, these points of the plot, the y-axis, gives you the probability of an observation happening, right? And it's also obvious from this plot that you will get the highest probability at x of m. So the idea is the number of occurrence of x of m is the maximum. Okay. And again, it is not a bad idea to mention that the standard deviation, sigma, measures the width of the distribution curve. So the larger the standard deviation, the larger the uncertainty and error will be, because we want to make this value, the probability of x of m happening, more and more and more, right? We want to maximize it to get a lower error. If you have this type of distribution, essentially it will look something like this. Okay, the probability of x of m happening is gonna be smaller than this. Okay, so what the ideal case is that your normal distribution looks something like this, with a very small distribution. Again, the most probable reading is x of m. We can of course use this formula to find the maximum probability you can get for x of m. The maximum happens at x of m. You just put the x of m here. This will go to 0. This whole thing will go to 1. and your probability of x of m, which is your maximum probability, is going to be 1 over sigma square root of 2 pi. And you have to keep in mind that p, the probability of x of m, is actually a measure of precision of the data set. So if your if this probability is closer to 1, it means that your data set is more precise. Of course, it means that which basically means that the standard deviation of the system is very small. It's close to 0. Okay, and that is the goal. That's what you want to. That's what you want to get as far as the measurements go. Yeah. Okay. So we have to go back to the point of the lecture. The point of the lecture is to find the uncertainty of your measurement. And essentially what that means is that you want to find the probability of something happening in a specific range, right? Later on, you will see that we will call this a specific range confidence interval. Okay, so you are given a confidence interval that they will tell you that what is the probability of something happening, or find the uncertainty analysis of something with a confidence interval of, let's say, 95%, which essentially means that what is the probability of something happening or lying, an observation lying here, right? And that will give you that observation. That will give you that that uncertainty of that specific data set. If you are familiar with the studies done in physical sciences, and by physical sciences I'm talking about natural sciences, but to say natural, like biology, or social sciences like sociology, all of these things. If you have ever read a study that in which they have presented a data set, you will see a lot of p-values. That p-value is essentially 1 minus your confidence interval, right? And the accepted p-value for them, they calculate this p-value, it's a whole phenomenon that's happening. The accepted p-value for them is 5%. So the analysis, if their data set lies within the confidence interval of data set lies within 95% of the confidence interval, they say it is an accepted data set. They present the results and they think of it as, they think of their conclusion as accepted or valid conclusions. Okay, but how can we find that the uncertainty of something happening in a specific range? First of all, we have to have the confidence interval, which we'll get to later. If you want to have the confidence interval of 80%, 90%, what should you, and what does that mean actually? We'll get there. But to find the probability, to start from the beginning, to find the probability of something happening in this range in a normal distribution, you essentially have to take the integral of your main formula, right, with respect to x, with these ranges from x of m minus x1 to the x of m plus x1. Okay, to make it a little bit easier, we come up with this new variable called eta, which is x minus x of m over your standard deviation. Then if you plug these values in this integral, you are going to get this. P equals to 1 over square root of 2 pi, integral of negative pi 1, eta 1 to positive eta 1, where eta 1 is x1 over sigma. So that will be your range, right? Exponential of negative eta squared over 2d eta. Okay. Using this new definition, we can tabulate the results and we can take the integral. You all already know that the results of this integral is an error function. So it's basically a complex integral to take. This is, of course, all of the scope of this course. But eventually what you can do is that because of this normal distribution, because we have a symmetry axis for this normal distribution, essentially, You can change the integral from negative eta 1 to positive eta 1, from this to 0 to positive eta 1, and make it even simpler and just multiply the integral by 2. You will get the same results. That's what you see here. And essentially, this integral is going to be equal to the error function of eta 1. So the values that the probability values we are going to see in the table in the later slides are essentially a representation of this value. Our calculation of 1/2 of error function of eta 1 over the square root of 2. Okay. These parts are a little confusing, and that's all right. It's just an introduction of what you're essentially going to do for the lab. So if you are not understanding, if you're confused about these parts, don't worry about it. You, of course, please reach out to me if you're confused, and I will try to explain them for you. We'll try to go over these together. But these things, the integrations, are not the point of the class. That's why I try to go as fast as possible, right? So we talked about this. Essentially, we are looking to find the probability of something lying within a range, within a distance from your x of m, right? Something I forgot to mention is that we try to normalize this probability distribution. We try to make sure that x of m is equals to 0 in these calculations. And you essentially, what you simply have to do is to calculate the x of m, your arithmetic mean, and just subtract everything from that arithmetic mean, and you will be all right. So this is the table I was talking about for different confidence intervals for different values of eta. As you can see, you can have different values for probabilities. You just have to make sure that this is, for example, this value is 0.41924. It is not 41,924. That doesn't make sense for probability distribution. So all of these values are essentially point something afterwards, and the value after the point is actually listed here, right? Okay. So how can we make sure that we are calculating the probability? Something that you have to keep in mind is that the range of the integral was x1 over sigma. Okay, so if eta 1 is 1, it means that your x1 is equals to sigma. Okay, so what does that mean is that you are trying to find the probability of an observation lying within 1 standard deviation away from the mean. So from here to here, for eta equals to here, for eta equals to 1. If eta is equals to 2, your x1 is essentially 2 sigma. So you are trying to find the probability of something happening within 2 standard deviation of the mean. Okay, and if your eta 1 is equals to 2, 3, then your x1 is 3 sigma. So you are looking to find the probability of something happening within 3 standard deviation from the mean. Okay, we'll come back to this table. So let's go from here. Let's say your eta 1 is 1. So you are looking to find the probability of something happening within 1 standard deviation from the mean, away from the mean. So probability of that happening is essentially you go back to the table, you find eta 1, this, okay. and then you have to multiply the probability by 2, mainly because we are looking at a two-sided normal distribution. So what some people do is that they look at one-sided normal distribution, so it's just the right-hand side, right? One standard deviation from the mean, right? This will give you the probability that is listed in the tables, but we are looking for the two-sided normal distribution, so you have to multiply whatever you read from that table by 2, okay? And of course, I'm pretty sure you can calculate eta 1 equals to 2, eta 1 equals to 3, which is 2 standard deviation and 3 standard deviation from the mean. For 2, it is 2 multiplied by this. We don't have the 3 in this presentation, but you will have the tables you're going to need for the report. So it's not a complete table here, but it doesn't really matter. Okay. Okay. So this actually value is equivalent to the confidence interval. Okay. So, like whenever I tell you that find the uncertainty with this confidence interval, this is the thing I'm talking about, right? So if I ask you to find something with the confidence interval of 68%, 68.3%, 0.3% or 0.683, you are looking to find the uncertainty of something, of an observation lying within one standard deviation from the mean, right? And so on and so forth. So this goes from less than 1 to higher than 1, right? And if you want to essentially make sure that you are covering all the bases and you are giving out the most confident results, you have to go with the confidence interval of 99.9, of course, which means that your observation is definitely going to lie at least at maximum 3.3 standard deviations from the mean. Please let me know if this doesn't make sense. I think you should be, you already have had a statistics course. We have talked about this a little bit in the previous year. So I'm just trying to give you a review of this. If you feel like you are not understanding this, make sure to reach out to me and we'll talk about this. Okay. So let's say I'll tell you the confidence level is this. You find the confidence interval, which is called the z-value, right? Or from this table, you can say this is the eta 1 value that we discussed, right? And then you present your data by just simply multiplying your eta 1, what do you call it, multiplied by sigma, right? This essentially is giving you that specific observation that we have discussed before, right? So that uncertainty of something happening is going to be the z-score multiplied by your standard deviation. Okay, let's have an example. Let's see if that's a... Yeah, let's have an example here. And this is essentially the same thing. It just means that your observation is gonna lie within this interval. Okay. Let's go to this example. Let's say you will have a mean of -4 and a standard deviation of 5.2, and we're looking at a confidence interval of 90%. So the interval, find the interval in which 90% of the population lies within your measurement, essentially. Okay. So 90%. We are looking at 1.65. That's the z-score or z-value, right? And this is how you present your data, right? -4 plus minus z multiplied by sigma. -4 plus minus 1.645. Let's go back to the table. 1.65 or 1.645, that's both of them work fine, and multiplied by 1.2, which means that your estimate is -4, your uncertainty is 8.554, okay, which is a very huge interval. But we don't know what the measurements are, what they are representing, so it may be very accurate or whatever. Again, you want to make this interval as small as possible, right? We're going to decrease the standard deviation. That's the goal post, but we will never get there. Okay. Next example, we are tasked with finding the probability that z is between 1.6 and 2.2. Okay. So the idea was the z-score essentially presents how far away from the mean you are, right? So what we need to do is to find the probability that something lies between 0 and 1.6. Let's go back to table. We have the 1.6, which was 0.4520. You have to read the first column, don't worry about the second column, the other columns. My pen doesn't work again. So let's go back to the table. Let's make sure we're on the same page. This 1.6, my pen doesn't work, so I can just draw here. Pen. Doesn't work anymore. Okay. Okay, I guess we just have to talk about it. You can, I am pretty sure you can find the 1.6 in the first column and then read the corresponding probability on the second column. So that's the probability of something happening of the z-value between 0 and 1.6. If we were looking at from negative 1.6 to positive 1.6, then we had to multiply it by 2. But in this example, we are only interested in 0 to 1.6 right here. That probability is 44. Okay, start working again. 0.4452. And if you do the same thing for 2.12, the z-score of 2, or eighth of 1 of 2.12, you will get 0.483. Okay, so we are essentially looking at the probability of something lying between, let's say this is 1.6, this is 0.2. We are looking at this probability, right? It's very simply, we just have to subtract these two, and we give you the probability of something lying here, an observation lying here. Okay, and that's it. Yeah, that's 0.03 or 3.7%. Okay, let's have another example. Please, 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 please reach out to me if you are confused and ask your questions. Okay, I will also upload this PowerPoint after this lecture. After this lecture is uploaded, and this is going to conclude our discussions on the uncertainty analysis. Okay, the next example is telling us a certain steel bar is measured with a device which has a known precision of plus minus 5 millimeter. So this is a way of telling you that 0.5 millimeter is the standard deviation. Okay, when a large number of measurements is taken, like, okay, how many measurements are necessary to make sure the mean length fall within the range xm plus minus 0.2 millimeters within the 95% confidence interval. Okay, so as I said, the standard deviation is 0.5, and this was the representation for a large number of measurements, if you recall, or the population. Let's call them the real population. But if you want to minimize the measurement, we are actually just considering a small sample. So this is how you represent the uncertainty. Z over the square root of number of measurements multiplied by the standard deviation. So we have the 0.2. We want this to be equals to 0.2. We have the sigma, which is 0.5. We have the confidence level, 95%. We can find the z-score to be 1.96 from the table, from the second table as the smaller table that we had. I don't want to go back there, but hopefully you know what I'm talking about. And for that, we can conclude that 25 measurements is enough number of measurements. Okay, we can apply this. This was actually the discussion we have had so far was for regular statistics, survey analysis, and all of those things. But if you want to do this uncertainty measurement, calculate the uncertainty in measurements, we have to identify a certain confidence level, and that uncertainty is usually represented with delta, capital delta. And the statistical method so far we have used so far is called the normal distribution, or the Gaussian distribution, or the z-score method, right? But if your data sample, so essentially you can use whatever we have used to find the uncertainty in measurement. But if the number of the data you have taken, the number of measurements you have taken is small, you have to use a method called the student t distribution. We are not going to go into the details of the methodology. You just have to know it was developed by someone called a student, which was a pen name for a chemist named William S. Gossett. The reason this guy used the pen name student was that he could not publish his method because he was under some sort of a contract with a beer company, and he could not essentially publish the method under his own name. He was not allowed, right? This method is mostly used with very small samples with a smaller number of measurements, and the delta, your uncertainty, is going to be calculated using this: the sample standard deviation, the number of measurements, and the t-score instead of the z-score. Usually what's the difference between the t-score and the normal distribution is that the t-score, a t distribution, is more conservative, meaning that the probability of your x of m happening is usually smaller than the normal distribution, and your standard deviation is usually, the sample standard deviation is usually larger. Okay, so we have to be able to calculate we have to be able to find calculate three different values. You have to be able to find the t-score from the table. That only depends on the sample size, right? You have to calculate a value called the degree of freedom, which is essentially sample size minus 1, very simple. And then you have to be able to calculate the standard deviation. Okay. So for different confidence levels and for different degrees of freedoms, this is going to be your t distribution, t student table, right? If the confidence level is 99%, 99.9%, and you have, let's say, 15 measurements, then your degree of freedom is going to be 14, and this is going to be your t value. Okay, very simple. Just plug that in and you'll get your estimation. Here we have an example. Let's say we have made an observation of the voltages. We have made some measurements of the voltages. The arithmetic mean of the voltages is 15 volt, and the standard deviation of the sample is 0.1, plus minus 0.1 volts. We want to determine the uncertainty, okay, at the 95% confidence interval. Degree of freedom here is 9 because we have made 10 measurements. Okay, so 10 minus 1, 9 here, and the confidence interval is 95%. So your t-score is going to be 2.62. Okay, so the uncertainty simply 2.62 multiplied by 0.1 over square root of 10, and it is 0.0715 volts essentially. So we can have a representation of the true value of the measurements with the estimate, which is V of M, and the uncertainty at the 95% confidence level. Let's solve another example. Let's say we have 10 measurements of the thickness of a metal plate, okay, which is given by this. We want to determine the mean value and the tolerance limit for a 90% confidence level. The first step is, of course, to find the arithmetic mean value. It is, if you do the calculations, you can find it to be 3.617, and the sample standard deviation, we also have the formula for it. It's going to be 0.0125. The degree of freedom for this case, since we only have 10 measurements, is going to be 9, and then with the 90% confidence level, your t-score is 1.833. Okay, so you can essentially find the uncertainty or the tolerance limit, and this is going to be a representation of your measurements. Okay, you may ask yourself, when should I use the Z method, the Z-score method? When should I use the T-score method? It is very simple to answer that question. Essentially, when you have sample sizes with smaller than 25, you have to use the T-score method. But after you increase, or when you have an unknown population standard deviation, when you're using only the sample standard deviation, but this part doesn't really apply to us because we don't really deal with populations that much. We only deal with samples. Okay, but then again, if you have a larger sample size over 25, the t distribution and z distribution are gonna be essentially the same, right? Because the t-score and z-score is gonna be the same for larger degrees of freedom. You just have to keep in mind, for a smaller than 25, you have to use t distribution. For larger than 25, doesn't matter, you can use either. And the last part of the lecture for the uncertainty analysis is the propagation of uncertainty. As you may be aware, essentially the lab is to measure different sides of a metal block 30 times and calculate the uncertainty for the measurement of each side, and then they calculate the propagation of uncertainty to the calculation of volume. Okay. So we have to make sure that we know how to calculate the propagation of uncertainty. As an example, let's say exactly the same example that I was just talking about. Let's say your length is this, your width is this, your height is this. You have the uncertainty, you have this estimate, but your volume, what is the uncertainty of the volume calculation? That's something that we need to discuss. It's pretty simple. You just have to use an equation for it, right? To find the propagated uncertainty for the volume. Okay. Let's say the uncertainty of each measurement, length, width, and height, for example, are these W1, W2, and here we only have 3, so W3. This R is essentially your eventual function that you want to use. So R here is equals to volume, which is height multiplied by, or let's say X, Y, and Z. X multiplied by Y multiplied by Z. Okay. So for the first one, you essentially have to take the derivative with respect to x1, which is x here. So your propagated uncertainty is going to be equals to yz here in this multiplied by w1. So the uncertainty in the x level, let's call this length. Okay, this uncertainty squared. Let's do the same analysis. You're going to get xy w2 squared plus x, I'm sorry, that should have been xz plus xy w3 squared. That's it. That will be your final uncertainty that you can just apply and use in this for this specific test that we are going to do. Okay. We can do the, so multiplication is actually the hardest part. Subtraction and addition. Then your function f of x and y is x minus y. You just have to take the derivative with respect to x once, which is going to be 1. With respect to y once, it's going to be 1 again. So if you go back to the formula, you write that formula down, you will see that if you only have x and y, for subtraction and addition, your propagated uncertainty is just the square root of, I think I forgot the square root here. Yeah, this is the square root of whatever. The square root of w1 squared plus w2 squared. Let me just, yeah. And this is if you are dealing with subtraction or addition. Multiplication or division are a little harder. We have the examples here. You make sure to study these if you are not clear on what to do, and please reach out to me if you have any questions. So that's it for the lecture of uncertainty analysis. And please let me know if you had any questions. Hopefully we are going to do this lecture, this lab on Thursday. That's the upcoming Thursday, not tomorrow Thursday, but the Thursday, September, I think September 3rd. It was September 3rd, right? Yeah, September 3rd, Thursday, September 3rd. But before that, we will, me and your TAs, we will record the lab, and we will upload the recording of the lab online. You are always welcome to participate in the lab or watch it online as use the data we are going to provide to write your lab report. Have a good day. Hopefully I will see you guys pretty soon.